Welcome to the first video meant to accompany the notes uploaded for April 6th. It is on stress combinations and the effects of their multiple loads on things. In this video, we'll start up the idea of adding stresses, and we'll begin a simple example problem. We now use superposition to solve for reactions of indeterminate structures. So we're very familiar now with how, if we have multiple loads on something, the reactions and the forces inside of it, forces and moments and internal things, will be just the simple sum of all of the different effects summed together, so long as we remain in the linear elastic region for the material, and we remain in small deformations with our structure. So that can carry over into this topic, which is on combined loading and the stress effects of combined loading. For example, let's consider this extremely simple example. We've got this very simple cross-section. We don't have to worry too much about the second moment of inertia. And we have both moment and an axial load. Well, we know that the axial load is going to cause a constant or a uniform distribution of normal stress. Right? We know that we can absolutely count on it. And I'm going to call this the normal stress due to axial loads. And it's going to be P over A, the force over the cross-sectional area. Similarly, by now I'm sure you're all agonizingly familiar with our equation for the normal stress due to bending moment. We've got some bending moment right there. And the normal stress for the bending moment, sigma bend, is going to be equal to the moment that's applied times the distance of the point being considered is from the neutral axis, divided by the second moment of inertia. And the stress distribution for this beam under this loading is going to be simply the sum of these two things. Pretty easy. Let's think about that now. And do it. I mean, like draw it out. First, let's think about the distribution due to the normal stress. That will be the easier of the two. We'll have the normal stress due to the axial load is the force over the area. In this case, it's going to be 4 kips divided by 1 kip, or 1 inch times 2 inch is which is going to be, 2 KSI. Alright, now, for this we'll need, for the bending stress, we are going to need a second moment of inertia. Let's go ahead and find that now. It will be base times height cubed over 12 for a rectangle, which will be 1 inch times 8 inches cubed. Sorry for skipping that step. Presumably you can figure out what went on there. divided by 12 is going to be 2/3 of a quadric inch. What a delightful unit. So we've got that now, which means that our maximum bending stress is going to be maximum bending stress. That's a lot of subscript. But that's going to be, well, 6 kip inches times 1 inch, because the neutral axis for pure bending on this is going to be, the middle, divided by 2/3. So that's going to be, what is that, 9? Yeah. 9 kips per inch squared, which I've decided to write as kips per inch squared instead of KSI. Very cool. That's the same thing. So that's our maximum bending moment due to that, and this is our normal stress. Now, because we've applied this normal stress, normally we wouldn't even draw this, but let's draw the stress distribution due to our axial loads. I should have put axial stresses in one color, and I'm not going back. So if this is our face, which I'm going to make 6 squares, because that's how big that is, then our uniform distribution of stress due to the axial load is going to look like this. And this is going to look like a very silly drawing, and you're going to wonder why I'm making it. We're drawing it like we cut right here, and we're looking at the left portion. So our distribution of stress is going to be uniform across the cross section. It's going to be 2. KSI. Now let's look at the stress distribution of bending stress. We didn't necessarily have to find the max, but it is going to be a linear relationship, right? It's going to be, as we move away from the neutral axis, which we said was at the center of this, because we've got such a simple cross-section, we're going to increase. So really, instead of this 1 right here, we could do y. We didn't have to solve it all the way. So that distribution is gonna look like this. At the bottom, it's going to be causing tension just like that. Or just like we had elsewhere, because of how that's going to be rotating. Let's draw it like that. That's not to scale. 9 is substantially more than 2, but let's not make it... well, let's make it a little silly looking. So this right here is our distribution of stress due to the moment. Down here it's tension. up here, it's compression. So I'll write plus 9 KSI right there and minus 9 KSI right there. Okay. Result. And then we can sum these to obtain the proper distribution of stress in this cross-section due to these two loads. All right, so in that case, because we're applying this this tension on top of this, this is uniform, pretty easy. This is just gonna slide in this direction. Okay, it's just gonna slide up. All of these numbers are going to increase by 2. Or basically adding a constant here, or if you like, changing the constant if you want to start down here at y equals -1. So our new distribution, which I will draw right here, is going to go from -11, which I'm going to draw right there, or from +11, I should say. Sorry, +11. I think I said -11 just now. +11 right there, at the bottom, and at the top, -7. Alright, so this means that the location of the neutral axis has changed. Remember when we talked about bending earlier, and we said that the neutral axis was the fiber where there is no stress or strain. That's going to be occurring, in this case, right here, right in the middle. And that's how it's usually been. However, now we've shifted it up because we've got this distribution, -7 KSI and +11 KSI, because that's what 9 plus 2 is. Alright, and this distribution, so it is frequently important to know what the location is of the neutral axis. You may recall when we did concrete and composite materials that not everything behaves just as the same in tension as it does in compression, and so the location of the neutral axis now is going to be even trickier than it was at that time. All we have to do, though, to find this neutral axis is say, let's scroll this up so that you can see, that the location of the neutral axis is going to be where this is stress is 0, and so that's going to be so let's just write down our stress equation. And the stress as a function of y has to equal 0 for the neutral axis. And that will be our stress equation for all of this cross-section. It will be -7 KSI if we're moving in this direction for y, plus 9 kip per inch cubed times y. And that is going to give us that y, wake up, come on, don't do this. That will give us that y is equal to 0.777, repeating, and that's going to be inches down from there. You could also, I guess, have gotten that it is 0.2222 repeating if you wanted to know where it is in relation to where it was. So this was a particularly simple problem, but it really shows the change in the distribution of stresses on the cross section. Let's consider a more complicated situation, though only slightly so.